Good morning, everyone. Welcome back to today's DCG lesson. Hope you all had a nice weekend. I know that with the kind of increased measures with the moving around, it's probably a little more restrictive for you, but hopefully you found some time and space to relax and enjoy the weekend and the good weather that we had, and that you're refreshed now and ready to be back doing a little bit of work. Okay? What I'm going to be covering today is I'm going to be covering structural forms, which is an applied graphics topic. It appears as question C2 on the exam paper, so that's section C of the exam paper, and it'll be question 2 in that. Now, what I'm going to do here is I'm going to do a kind of like a worksheet today, and I'm going to focus on the primary shape constructions only. Now, so for example, that would cover, say, the part A and B in a question in most cases, and the part C or D, I'm going to leave them off for the moment. I will be doing examples later on where you can see some of the exam questions done out. And if you look back through the resources that I have available on the YouTube channel, go back into the DCG playlist and scroll down to structural forms, and you'll find digital resources in relation to the part C's and D's, okay? But I think from the outset with these questions, it's really, really important that you understand the type of shape you're drawing, you're able to identify it from a question, and that you know how to actually construct it properly. Now, here, not all variations or methods are covered on this sheet, okay? So what I'm giving you is a snapshot. I'm not giving you absolutely everything here, okay? It's just not possible for me to do it in 40 minutes, all right? And it should take 40 minutes today to get through all of this properly. So, look, guys, you'll see with exam questions, there'll be a variation on a mixed method approach and so on, but I'll only be able to deal with that in the context of an exam question. And I'll deal with that as we go along down the line, okay? So for the moment, we'll just focus on what I would identify as the 3 types that we have within structural forms, okay? We have the hyperboloid of revolution, get to that in a second, hyperbolic paraboloid, and the parabolic translation, okay? So these 3, typically speaking, in one form or another, are a little bit mixed, tend to come up on the exam. Now, interestingly enough, the hyperboloid of revolution itself in its traditional form hasn't been up in a while. I'm not making any predictions or guesses, but I would say if you're going to do this area of structural forms and in preparation for this year's Leaving Cert, it might be no harm to do 1 or 2 more of these particular types in preparation. It could come up. I don't know, but just be prepared anyway. Okay, likewise with the rest of them, but you know, if I was to say this is an area you could do an extra 20% in, I'd put it into this one. It's a gamble, but look, we'll see anyway. So I'm going to take you here into hyperboloid of revolution, okay? So as we look here at the sketch first, all right, you'll see here this type of shape. Now, typically speaking, you see that type of shape, like, for example, architectural structures such as cooling towers at power plants. And if any of you have had the unfortunate experience maybe of been dragged around IKEA up in Ballymun, then you might have noticed on the way in on the left-hand side of the motorway, if you're coming from a kind of a southbound direction, you might notice that there's a water tower just before that exit, and that's a hyperbolic or a hyperboloid of revolution structure as well. Quite a nice one, concrete structure, and so just, you know, you can see it in everyday life. We can see these structures around us. Now, what's special about these? You know, they're, you know, curved surfaces. You know, some are doubly curved. You can see here that I have highlighted some of the parts here of the actual hyperboloid of revolution. We have the top circle, we have the bottom circle or the base circle, and in the middle, halfway up, we have the throat circle. That throat circle is really important for us, especially with the method we're going to use, because it is the circle that has the narrowest radius on the actual hyperboloid of revolution structure. All right, generally speaking, it's halfway. Okay, so if this was 200 tall, that throat circle is going to be located 100 millimeters up. All right, now what's the significance of this? Okay, the significance of the throat circle for us here is we will be using it as a guide to applying what's called the tangential revolving asymptote line. Okay, and that'll be our method. the tangential method. Okay, now you're probably just heard a word there called asymptote, and you're probably going, what the heck is an asymptote? An asymptote is a straight line that continually approaches a given curve but never meets it at any finite distance. So really, it's quite a sad story, because the curve and the line, they get so close, but they never actually get the opportunity to meet. So to infinity, if we had a curve here and we had an asymptote, which is a guide for the curve, the asymptote would be like a straight line, the curve would be curved, and they would, to infinity, they would get closer and closer and closer, but they would never meet. And if we went all the way down to the level of looking at it through a nanoscope, there would be, you know, atoms and you know, quarks between them that would never meet. Okay, now, so I'm going to take you just directly over here. Going to zoom in a little bit, and we're going to get to this particular section that we have here. Okay, let's zoom out a little bit more. There we go. All right. So here, tangential method to finding hyperboloid of revolution. Given the top bottom circle, radius equals 45 for the top bottom circle. Okay, that's that one there. And then the throat circle has a radius of 20. They're just two I picked for this. You can replicate this in your own time then as a result of that, and everything should work out okay for you. So, and that's in the plan view. True length of the asymptote and elevation is given as 150 millimeters. Now at the moment that means very little to you. Okay. What I would say is what I'm presenting to you here is I'm presenting, as opposed to giving you the height for the hyperboloid of revolution up here in the elevation, which I have drawn lightly, and I'm going to kind of uncover all of that now with the method in a minute. So don't worry about if you can't see anything here. I'll just have shaded in and done lightly, and I'm going to heavy everything in. You could be presented this information in elevation in two ways. You can be given the full height of it, which means that's grand, because if we have the full height of the top and bottom circle, and halfway would be the throat circle, and they could work things out from there. Or you could be given the true length of the asymptote. All right, and that will be written in the actual text part of the question. All right, so this is what I'm giving you here, and I'm going to show you how to find the height of the hyperboloid of revolution given the actual length of the true length of the asymptote. Now, what's the asymptote? We're going to get to a bit of drawing here now, okay? So, what we want to do, and it's called, we'll call this the tangential asymptote method, okay? So, in the plan view here, I have my circles, all right? I'm going to focus on the throat circle. What I'm going to do is I'm going to draw a line that is tangential to the bottom of the throat circle, okay? And that line is going to reach right across to hit the top and bottom circle there as such. And we'll call that point A, and we'll call that point B. And just as a matter of interest, you can YouTube or Google hyperboloid of revolution and put in GeoGebra after, and you'll get a sample of what this actually is. Because what we're going to get here with this line, this is the plan view of the asymptote, okay? So I'm going to write this in tangential asymptote. And of course, we've just talked about what an asymptote is. So that's our tangential asymptote line here in the plan view. It's touching the very bottom of the throat circle tangentially. Okay, straight across gives us point A and B. Now, if we were looking in plan view, that appears like that. If we're looking in the elevation, all right, we'll see it in a minute. But if we just take a look back at the little sketch here, that pink line AB, this is actually the line I have here. Let's say that's point A, and that's point B down there. Okay, and this point here will be that point there. Okay, so that's kind of looking at it in a 3D view. And what's going to happen is this line is going to rotate. All right, it's always going to be a tangent to the throat circle, so that it's going to be rotating around the throat circle, and as it does, points A and B are going to be forming the shape for the top circle and the bottom circle, and as a result, that asymptote line is going to guide our curve that's going to form as a result. Okay, so we'll play that out now here in the actual 2D solution. So what I'm going to do is I'm going to take points A and B now directly up into the elevation itself. Okay, just I'm going to take them straight up, and you'll notice that I'm drawing them particular lengths. That's because I have some of the lengths pre-marked. So you just, when you're bringing them up, just draw them on up and draw them lightly. Don't be worrying about them, okay? Again, I would use a very light color to draw them up. So I'm going to take A and B straight up, okay? So let's say I start at point B here, draw a line straight up, like so. Don't worry about the length of it, as I said. Just draw it up, and likewise here for point A, okay? And draw that on up. Okay, now, so what I have here, essentially, on the XY line, I have, let's say, if I wanted to call it, let's say point B is on the ground and point A is up in the air. I have point B here, okay? Now what I want to do is I want to find point A. As you can see, that line, as we look at it in the 3D view, it's kind of like a diagonal line. It's not straight up, okay? So we want to find A, but we want to find the diagonal line. So what we want to do is we want to go back to that information that they placed deliberately into the question, so that if this type of arrangement comes up, that, you would know that this bit of information applies here now. So what I'm going to do, on my compass, I'm going to take 150 millimeters. So I take from 0 out to 15, which is 150, like so. Get that out of the way, put it on point B. And what I'm going to do is I'm going to swing it to hit the line I brought up from A. Can you see that? There's the line coming up from A. I'm going to swing an arc to hit that line. I'll make it nice and apparent. You can see that arc there. That is point A located up here in the actual elevation. So now, what I have, guys, is I have the asymptote line here in the elevation, and we're going to, and that gives us the height for the elevation as well. So there's my elevation of this line, AB, okay? AB, that's it in the elevation. That gives us the height. If I measure the direct height of that there, gives me a height of like 126 millimeters or something like that. But that's irrelevant. We're just going to work on with this now. What I do need to do is I need to project that top line across there, like so, okay? So that'll represent the top circle, all right? And I'll just bring those points up from the plan view now, okay? From the circle there, the outside of the circle now. Just forget about the asymptote for the moment. And bring up the outside line from the circle there as well. Remember, I have all these lines kind of pre-marked lightly, so if you're wondering how they're kind of working out, let's say there's the top circle up there, okay? That's lovely. What I want to do is I want to recreate the asymptote line, but going in the opposite direction now, okay? So, in order to do that, well, sure, I have point A is here. I have it brought up, okay? Here it is here, and I have the point B to here. Okay, so that's where it hits the top line and where it hits the bottom line. We can just join them across as well. So we get like an X in the elevation, okay? All right. And that X is going to give us the exact center point here, okay? That's why we would kind of do that, as well. We could get away with doing one of them, and then when we get certain points, we could mirror them. But I'd rather show you this full way first so that we get two asymptote lines, all right? I'm just going to write in asymptote and asymptote. Really, lads, that's the same line. We just draw it in two positions, all right? So it's not like there are two separate lines. We just have the one line, but I'm just showing you it going in one direction and going in the other because we want to draw this thing in 2D, okay? And it's just going to help us with things along the way. Now, so there's my two asymptotes, all right? Now, what we want to do is we want to mark in our throat circle line here, okay? So as we see the throat circle, it's just going to be a straight line, and it's going to be the same width as the plan. So we're going to project up the width of the throat circle from the plan view now up, and we're going to draw it up to meet the line here going through the center point. So we'll put that in as a, okay, and I'm going to draw up the throat circle. Okay, like so, okay, so that's the width of it defined there. So, and coincidentally, all right, there are 2 points that are going to be on my hyperbolic curve that I'm going to get on this side and this side, and likewise the points that are contained on the very edges of the bottom circle and the top circle. Okay, so that point there and that point there. The points on the asymptotes themselves, they're never going to be on the circle or the hyperbolic curve, as we said already. The curve and the line, they never meet. The line acts as a guide for the curve. Now, how do we go ahead and actually find the curve itself? What I'm going to do is I'm going to focus in on the plan view here. So I'm going to zoom in a little bit there so you can see a little clearer. Now, I'm going to take half the line here, okay, in the plan view of the tangential asymptote line. So I'm going to go to the point here, all right, in the plan view at the bottom of the throat circle, all right. We can call that point P, okay. Let's say that's point P. I'm going to divide up the portion of the line PB into 5 equal parts. I could do 6, 7, 8, 9, 10. I could do 1,000, but I'm just going to do it into 5 equal parts. What I do normally when I do this, guys, you know, I'd measure the line first, see is it equal? Okay, actually it is. It works out equal. Okay, so it's 40 millimeters long. All right. Now that's a coincidence. So what I'm going to do is I'm going to go back. All right, just in case, because in an exam situation, if that line doesn't divide evenly, we want to apply the proper process. So I'm going to divide that line up very quickly, draw a line at a random angle, mark 5 equal parts on it. So I've drawn a line at any angle there, and I've marked out 5 5s. I'm going to join the last point into 8. Okay, and then each of the points after that, sliding set squares, draw them at the same angle. Okay, I have them already pre-drawn very lightly, so I can just extend them on. Okay. And like so. Okay, so I have those. All right, I'm just going to give them a darker dot there so you can see those points on the line PB now. All right, now I would label those points. All right, I call that 1, 2, 3, 4, and then B, obviously. Okay, now this is really important because what essentially we're doing here is we're taking, for example, the asymptote on this side. All right, we're taking this part of the asymptote and this part of the asymptote going in the opposite direction. Okay, in the elevation. I'll just zoom back out now so we can see there. Okay, hopefully that's clear enough to you. And get that straight. Lovely. So what we're going to do is those points are going to be located on the asymptote line, but they're also going to help us find the actual shape of the curve itself. Okay, and I'm going to show you how we make all that happen. So I'm going to take points 1, 2, 3, and 4 straight up now first to hit the asymptote lines. All right. So 1, 2, 3, and 4 straight up to hit the asymptote lines. So there's 1, and I'll take everything up in blue here now at the moment. Okay, so you can follow that. So apologies if you're colorblind, but I will reference the numbers as well. So this is the line for 1. Is there now? My T-square is just a tiny bit off for some reason. No. Okay. So there's 1. Bring 1 on up. Lovely. When I bring 1 up, straight away, guys. Straight away, don't delay. Just mark 1 and 1 very lightly there. Now, they're not the points that are on the curve, but they're very important to finding the points on the curve in a moment. Okay? 2. 2 and 2. 3. There's 3 and 3. And then 4 and 4. Make sure that's lining up okay. Lovely. All right. And that's 4. And that's 4 up there. Okay. Now, what we want to do is we want to locate the points in the curve. So we have to get our compass here in the plan view. And what we have to do, put it on the center point of the throat circle. Well, actually, it's the center point for all the circles in the plan view. And I'm going to measure down to the point 1 here in the plan view. Okay. So from the center point out to point 1 on the line PB. And I am going to rotate that point around to hit the center line of the circle. Okay. I'm going to repeat that for point 2. I'm going to repeat it for point 3 and repeat it for point 4. So what we're doing now is we're rotating the points from the asymptote line onto the center line for the hyperboloid curve. And that's the crucial thing here, because what we're going to do now is we are going to project out our lines for starting at point 1. I'm going to project a line out from 1 and a line out from 1 like so. Okay, show you. Now you're probably wondering, how far does that line go out? I have it pre-marked. It goes out as far as the line that you draw directly up from the point 1 that you swung around onto the center line. So there's 1, 2, 3, and 4. So these are the points that I am now focusing on taking it up. Okay, hopefully that makes sense to you. So what I'm going to do is I'll take them up in blue, or no, I'll take them up in the light pink line as well. Okay, so bring it on up, and it hits the lines coming out from 1 and 1, and what it does is it gives me the point 1 on the curve itself, and I'll make that 1 a little bit bigger. Okay, I'm going to do the same from point 2. So I'm going to bring a line out from point 2 in the elevation and 2 in the plan view. Again, item pre-marked, so if you're drawing them, just draw them out any length you want really, guys, but just draw them lightly. Okay, and I'm going to draw up the point here from point 2, again using the light colored marker here, just so you can, things don't look too messy, because you'll have a few lines, but it's all very repetitive work. So there's 2 and 2, and you can see the curve beginning to form now. Okay, and then we'll go to 3. So I'm just making sure 3 is there. I'll project 3 out like so, and likewise there. Sure, I'll do 4 as well while I'm at it. Okay, so again, they're all been projected out. Just put a little arrow there straight over. Okay, and then I'll go to 3 and 4 here in the plan view, and I'll draw them up lightly. Okay, so there's 3 there and 3 there, and I'll mark them immediately. And as you can see, lads, I'm very consistent with my labeling when I do label, because, you know, I loved drawing in school, but it never came easy to me. I had to work at it. All right, I really did. But I really enjoyed learning new things and trying to understand. And to be honest with you, labeling was one thing that really helped me. Okay, right. So now I have all the points here, and I just want to draw that curve in. Okay, so starting at the bottom point here on that we located on the bottom circle, the very outside point, we're going to draw a curve connecting all our points all the way around. Okay, we can call that point P there. Okay, so that will be P in the plan view. So just very lightly. Now, there we go. I have the curve done on one side. Now, what I would do, guys, is draw a line directly across from each of the points that you've just found on the curve, mirror them over to the other side. I'll mirror one point here just for the sake of it to show you, and then what I'll do is I'll actually, so let's say I take point 3 here, compass on the center line. Okay, maybe I should highlight that center line a little bit better. Apologies about that for those of you who might have been a bit confused with that. Okay, and what I'm going to do there now is I'm going to put the compass on where the line 3 passes through the center line, measure back to point 3, which is on the curve, okay, and swing it over to the other side. Okay, that gives me point 3 over here. Now, I've all the points already brought over, so I can just mark them off here and complete out the curve on the other side. 2, 1, P, 1, 2, 3, 4, and then A is up there anyway. So I'll take my curve back like so, and again your curve, a little tip when you're drawing curves, guys, if you have points, already marked out on the curve. The simplest way to draw the curve then is not to look at the top of your pencil, but to look at the point that's directly ahead of you. So if I'm drawing the curve, I'm always looking 1 point ahead. Now, you might think, well, that's a little bit, you know, shouldn't we be focusing on the pencil? In the case of the actual drawing a freehand curve, look at the point ahead of you. All right, same for an ellipse or a parabola or whatever the normal ways. Just try it and see if you can draw a more accurate curve as a result. It was a real eye-opener to me. I remember when I was in school, I'd be looking at the top of the pencil and I'd be pressing it into the page and it'd be wobbling and the whole lot, and it'd just look messy and untidy. But then I learned that method of just looking at the point ahead all the time as the pencil was moving, and the pencil will follow your eye line. Okay, that's the beauty of that. Now I just, as usual, a little bit of color, and you can see there that that method, quite simple, guys. All right, once you break it down into the little steps that you have to do, it's real simple. Now, what else could you be asked in that question in an exam? Well, it could be cut at an angle. It could be you could be asked for a set of planes to it, a plane director, whatever. Okay, that stuff I'm not going to cover today, but you could be asked for a cut surface or an end view or so on. All right, but that's the hyperboloid of revolution. Okay, and hopefully that has been some help to you. And what I'm going to do now, won't delay, I'm going to move on now to the hyperbolic paraboloid. And we'll just zoom in on that now. Okay. Now, hyperbolic paraboloid. What's it all about? Well, as opposed to the hyperboloid of revolution, all right, the hyperbolic paraboloid, it's a doubly curved surface, okay? It's, as I call it, the Pringle-shaped or saddle-shaped surface, all right? And I'll just autofocus that there, because there we go, and we'll lock the focus. Lovely. Now, so in this example, right, look, we have this Pringle-shaped, saddle-shaped surface. I have a little sketch here, all right? Let's say that's like a Pringle. And on the Pringle, we generally are given 4 points, or it could be 5, depending on the shape. This one is fairly symmetrical, all right? But we're given points A, B, C, and D, all right? D and B here are basically the length of it, and A and C are the width of it, okay? So front to back, side to side, okay? And these lines here, they're called element lines, all right? You'll see them in an exam question. They're given as a dashed line, right? They're actually called element lines. And these elements are what we form this shape around. Now, in the instance of this question, it says, in this example, we are given the elements A, B, C, and D in elevation and plan. The outline shape of the Pringle in plan is an ellipse. So you can see here, I have the ellipse already pre-drawn in. I don't think you have to go into an ellipse, but I will tell you about the shortcut, all right? First, you want to identify what the major axis is. That's the line AC, okay? In the case of this question, I think I have that as 70 millimeters, so to be a radius 35. And for B and D, I have it as 50 millimeters, that'd be a radius of 25, okay? If you want to go ahead and draw it. So you can see here, I just picked 1/4 of the ellipse, all right? So I just drew 1/4 of the ellipse. There's 1/4 of a minor circle, 1/4 of a major circle, and I've done my 60 degrees, my 30 degrees, done my triangles, got my points on the curve, and then I would mirror the points just like I did over here in the hyperboloid question a moment ago. Mirror them through the center line this way, and then mirror them that way and back down that way. That's going to save you a little bit of time, and lads, we're all about saving time, especially in an exam situation, okay? So what we're, this center point here of the hyperbolic paraboloid, you know, we'll call it point O, but what it actually is called the saddle point. It's the very middle of the point. So you can imagine a saddle on a horse, the very middle of the saddle, that saddle point is the very center of the surface, okay? So we just want to bear that in mind, all right? Now, what we're going to do here is we're going to, as I said about saddle point, we're going to find the hyperbolic paraboloid surface. We use a series of parallel or equally spaced section planes that cross each other, Okay, now what does that mean? Well, you're going to see in the plan here in a minute, I'm going to divide up this area here, A, B, C, and D, okay, with a series of parallel lines going one way and a series of parallel lines going the other way. And it'll look like a kind of a mesh, if you want to call it, okay? That mesh is like the fabric of our surface that we're going to form. Because this is a doubly curved surface, it's a surface that really can't be developed out because we don't have any particular true shape that we can reference on it. But we can certainly reference points on the surface, and this is what we're all about here. Points and lines that are going to give us the shape of that surface, okay? As opposed to trying to find the surface itself. We will get that by default, okay? So these lines that are going across, they're actually like planes, okay? If you want to call it like that. Section planes. Now, section planes are, if you've used SolidWorks, you know, when you offset a plane from a plane, well, imagine a whole lot of planes been offset from each of the lines that we have here already, like AC or AD here, offset a plane 10 mil, 10, whatever. What we want to do is we want to divide up the line, though, equally on each of the lines here. So pick a number of parts. I wouldn't go any lower than 5 parts on these ones because you want kind of a nice accurate curve. The more points you have, the more accurate it'll be, but 5 is enough, I would say, in most cases, all right? Unless it's a really big drawing, you could go up to, you know, 6 or 7 or 8. I wouldn't be going beyond that, okay? You're only creating work for yourself. And again, you know, it's not about how much you do. If the method is correct and you use 5 points and do it well, you get the marks for it, okay? So don't worry about it. Now, in the case of this question, A, B, C, and D, they're all the same length, okay? No problem. In some questions, though, you might have A, B one length, B, C another, and so on, and the shape would be irregular. It wouldn't be like what we have here. In that case, what you'd have to do is divide each. If you decide 5 parts, you'd have to divide each of those lines individually up into 5 parts and connect them across, okay? So that means that the points on each of the element lines are relevant to each other, okay? Whereas here, it's quite straightforward for us, all right? I'm picking the line CD here. I've already divided it up into 5 equal parts. You can see my construction here. And all I'm going to do here now, guys, is I am going to draw those lines, okay? Parallel to the line AD, okay? Sliding set squares, draw them directly across to the other side, okay? Like so. So I only have to divide up one line here. Now you might go, well, oh, wait a minute, I have to divide up this line because I have to go this way. No, take your distance from here and step it across to here. Just get your compass, put it on D, measure out to 1, and swing it around to hit the line here. And then step it out another 4 times. That's all you have to do there. So that's all I've done, all right? So I don't have to go dividing up another line, okay? Again, we just want to be smart and efficient. That saved me about 30 seconds there, all right? And there we go. So you'll see here now, in my plan view, I have this kind of mesh, and you can see that on the mesh, these points all kind of line up there on the center line there, okay? Now, great. What I want to do is I want to project those points up into the elevation, all right? So, for example, I'm going to take them up here from either the top lines here, or both of the top lines, in fact, and to hit the lines here, A, AD, and CB there, if you want to call it like that. So just project them up. Again, I'll do that with a very light marker, just so we can kind of limit the heaviness of the lines that we're bringing up all the time, because we're going to have, again, a few lines here. Again, we're finished. So I'm bringing the points up from where the grid hits the element lines, all right? And you can see here, like so. No big deal, lovely. And do the same on the other side, like so. And you'll be looking at this now and you'll be still going, how are we going to form a curve out of this? And this is the part of this that I think is really cool. Okay, so I projected those points up there, all right? If you wanted to label them, all right, let's say we call that, 1, 2, 3, 4, all right? And let's say we call that 1, 2, 3, 4, okay? You notice the way I labeled them kind of opposite, okay? Why? Because, well, if you're labeling it, it makes things a little simpler after. You'll see why. So I have here, I have point 1, and I have point 1, I have 2, and I have 2, I have 3, and I have 3, I have 4, and I have 4. They're all the points there, okay? And I'll just highlight those points a little more graphically there for you. Okay, So they're the points on the lines there. Great. I'm going to join 1 to 1, 2 to 2, 3 to 3, 4 to 4. That's going to form my curve. So when I join 1 to 1 here, right there, a little bit of a wobble in that one. Now, as you can see, as those lines cross over each other, it gives me this surface here, the top surface. All right. And this, in fact, would be our saddle point right here. Okay. We could call that the point 0. All right. Now, in this case here, you don't have to go drawing a curve in on top of that. All right. What the lines have done is they have generated the general shape of that surface. If we wanted to draw a curve in, we would have to make sure that the curve was hitting exactly the halfway point between each of the little segments of the line, and that was tangential to it, and drawing it all around. Okay, but we don't have to go into that, right? That is sufficient what you have done there. Okay, now we still have the bottom curve to look after of this, and this is in relation to the elliptical shape now that's on the outside. So we've got the top curve of the top surface, which would essentially be this surface just in here. All right, and I know it's all one surface, all right, but now we want to get this perimeter curve down on the bottom part here, okay? So what are we going to do? Well, we're going to use what's called the, we'll use the extension method to find the under curve here in the elevation, okay? And this is fairly straightforward again. This time I'm going to use a green marker. What I'm going to do is I'm going to focus on this area of the drawing right here. I'm going to line up my line 1, 1 here, and I am going to extend on the line 1, 1 to hit the ellipse curve. So there's point 1. Can you see that right there? Point 1. I'm going to do the same with the line 2, 2. Extend it on. There's point 2. Same with the line 3, 3. Extend it on. There's the line 3. Here's the line 4, 4. There's the line 4. Okay, I'm going to bring those lines up now, and again I have them pre-marked, so if they just don't happen to work out very accurately, don't worry about it. All right, so I'm going to bring up the line 1 like so. Okay, and bring it up to line 2. Some of the lines might fall on top of each other as well, don't worry about that. 3 and 4. All right, and then here in the elevation, I'm going to go back to the line 1, 1, line everything up, and I'm going to extend the line 1, 1 onto hit the line I just brought up. There's 1, 2, 2, 2, 3, 3, extend it on out to meet the line coming up from 3. That's 3, and then 4, 4, extend it on out. 4. Then I'm going to mirror those points across to the other side. Okay, and again I would have just taken all these little, if I wanted to do that, bring across your projection lines. Okay, don't worry about the length of them. Okay, that'll all sort itself out in a moment. And then you can just say, for example, here's the distance from the halfway line. We'll draw in that halfway line a little bit clearer for you so you can actually see it. Okay, I will take my compass, put it on the halfway line where line 1 goes through it, and I would step 1 off on the other side. Okay, there's 1. Do the same for point 2 that I've just found. Okay, there it is there. Swing it around to hit the other side. There's point 2. Okay, and then likewise for 3. And then point 4, same thing. And swing it around. All right. Now what I have, okay, is I have the area or the points to form my undercurve. So I join everything around nice and light first. Okay, I'll heavy over that with a marker in a second. Okay. Now, there we go. And then I will heavy line around. Now, I know we're coming up on 40 minutes already, lads, but I'm trying to do the whole topic of surface geometry here. I just have one section left, so if you can bear with me, I greatly appreciate it. Again, I'll just apply a little bit of color in here, just so you can see the shape of that surface. Okay. and like so. Okay, and there we go. That is my hyperbolic paraboloid complete. What could be asked on that? Plane directors. We find the VTH, vertical trace, horizontal trace. And we could be asked to cut this in half, find a cut surface end view. We could be asked to cut it at an angle, find an auxiliary. We could be, a hole could be cut through it. Okay, this might not always be elliptical, that could be circular. You know, we can have a variation of things asked for part C and D on that. For the moment, that is the hyperbolic paraboloid. Now, finally here. Okay, we'll get down to the last one here. All right, and thanks very much for your patience, guys. We won't be long on this one. Now, this one, fairly straightforward. If you remember junior cert, you remember how you drew a parabola in junior cert, you're going to be off to a flyer with this one, okay? So what I have here is I have parabolic translation. What is it? Let's have a look at this shape down here. It's kind of like a shell type shape, okay? And the way these shapes are generally formed from a geometric point of view is imagine taking one parabola, okay, and then running that parabola along a set of other parabolas. So, for example, these dotted lines you see here, that's actually this parabola, which will be in the end view looking in here, all right? That's actually that parabola as it follows this parabola here, which is ED, and that parabola there, which is CD. So it's constantly translating, decreasing, decreasing, decreasing until it meets the horizontal plane, and that gives us the footprint, okay? And obviously this gives us the shape in that direction, and the parabola itself gives us the shape going in this direction as it's generating and translating, okay? So the main thing to identify here, we have an elevation, we have a plan, we have an end view. Most of this is orthographic projection, all right? Now, again, I have everything pre-drawn lightly. I'll show you how we do it in a second. Here's my end view, very important, all right? Now, these measurements, they could be whatever, okay? Doesn't matter. All I have is this shape, and I have one end of the shape here that's kind of cut, okay? And I want to find that little bit. I just want to show you a variation in the method. But what I want to focus on firstly in this question is your end view, all right? So my end view here is just a parabola. Normally in a question, you'll be given the width for the rectangle and the height for the rectangle, and we use a rectangle method. And you can see there, I've found my parabola. I've divided up 5 equal parts on the bottom, 5 equal parts on the side, and I have found my points as a result of using my parabola method. Great. I then transfer those points across from the side here to this line here in the elevation. And what I do, all right, which I'm going to do out now, is I'm going to find the parabola curve between D and B, and subsequently on to point E, which I don't have yet. I have an indication arrow here pointing in towards where E might be. I know the angle of the cut on that surface, but point E is somewhere on it, and we want to locate it. Okay, so I'm going to take across those points here from my parabola. Now I'm taking across the points that I use to divide up the outside line, because what I'm going to do here is I'm going to use the parabola method again. And I divided this line into 5 parts, so I might as well divide this line into the same number of parts. So I'm just transferring that measurement across, okay? There's no big deal with that or anything fancier behind it, okay? It is what it is, okay? Now, so I'm going to take those points now, and I'm going to draw them back to point B, because point B is the vertex. So you remember, the points opposing point B always get joined back to it. So there we go. All right, I'm going to join that back. Join this point back. Join this point back here. And this point back here. Fantastic. Now what I'm going to do is I'm going to divide this top line up. This section here from B out to the end of the rectangle right here in the elevation. So as that measures out from me, it measures at 60. So if I divide 60 by 5, each part will be 12 millimeters apart, okay? So these are the ones on the side, okay? They are whatever, and these ones here are going to be 12 millimeters apart. Or if you want, you can use your line division method. But if the line is equal, you might as well just divide it up evenly. Anyway, so that'll be the smart way to do that. Now, what I'm going to do is I'm going to draw those points now, okay? And you'll notice that I'm going to draw them all the way down into the plan view now, these points here, because I'm going to reuse them in the plan view in a few moments. So draw them on down, okay? Now, that plan view, I was given the rectangular outline for the plan view, so don't worry about that. Whatever it is, you just take your points and draw them down into it, okay? And don't worry about anything else. Draw them on down. There you go. Right away down to the bottom line of the plan view. Lovely. So I want to find the points here for the curve in the actual elevation here. So let's say that's 1, 2, 3, 4. All right, and we call that 5 or whatever, and or we go 1, 2, 3, 4, 5. Okay, fine. So 1 meets 1 right there. 2 meets 2. 3 meets 3. 4 meets 4. I know to put the numbers on the top. Doesn't make any difference. So what I'm going to do now is form the curve there. Nice and steady. Okay, lovely. Have the curve drawn in. Super. What I want to do now is I want to mirror that curve over onto this side until I get it to intersect that line for E. Okay? And like this is just a condition within the question. It's not actually something that's part of the normal method or at, and just throwing it in is like potentially you could have some sort of arrangement like that at the end of it, where you have to extend the curve on. Okay? So what I'm going to do is I'm going to mirror across a couple of points. So I'm going to take that point 1, mirror that through the line from going down from point B, and I'll take the point 2 as well. So I'm taking point 1 right here on the curve across through the line for B and 2, and what I'm going to do is I'm going to take the distance there from the line for 1, passing through, and step it over. There we go there. And then for 2, where the line 2 passes through the line coming down from B, and step it over, and there it is there. So what I get is, I'll draw it very lightly first, is that section of a curve there, and I only need the bit to where it hits the line there. Okay, and that is my point E found there. And then what I can do in the plan view is I can drop that point E straight down. Okay, so point E, drop it straight down now to hit the center line in this rectangular section in the plan view. And there's my point E found. Okay, great. All right, we have a point on the curve. That's super. Now, here's the method for finding the points here in the plan view. You can see I have very lightly a shape here. To find that shape, what we're going to do is we're going to focus on this portion here first, and then we'll focus on that bit after. All right, so this portion here first, we're going to recognize a couple of things. All right, we're going to recognize the individual heights we have. Okay, and when I mean that, I mean from the XY line up to the curve. And I'm going to use my original lines that I used for the locating the parabola. Okay, so those points 1, 2, 3, and 4. So what I'm going to do is I'm going to highlight here with arrows the individual heights I'm going to take here. Now you're going, heights, okay, right. What way are we going to use them in a plan view? So let's call this H1, H2, H3, and H4. Okay, I'm going to take those 4 heights now, and I'm going to mark them down from point B here in the elevation, because this is how we actually, this is how the generating parabola is translated. So this is our generating parabola. Now we're translating it using these individual little heights, but we're stepping them down from the top point always. Why? Because the height of this is going to decrease as it translates and moves towards the ground along the profiles of the other curves. Okay, and of course we want to find the profile of the CD and AD, that curve that kind of goes around as the footprint of it as we look down in plan. That's what we're going to find as a result of this. So what I'm doing here is I'm going to mark down now my individual heights. You can take them with a compass, or you can measure them whichever way you want. You can measure with a rule. Let's say I take H4 there. So from the XY line up to where H4 hits the curve, take that, and you're going to step it down from point B, okay? So I have that there, and immediately what I'm going to do is I'm going to put a little arrow there, and I'm going to go H4 straight away, all right? Then I'm going to go to H3, take the distance for H3 like that, step it down from B, and then I'm going to do the same thing, except this time I'm going to mark H3. Next one, H2. Take H2 on the compass, mark it down from point B, step it off, then mark H2, and then finally H1. We haven't long left now, lads, all right? H1, mark it down, arrow H1. What I'm going to do is I'm now going to project a line, okay, where H4 is marked there, horizontal line straight across, okay? Like so. H3, same thing. H2, same thing. H1. Now, I only have to do this on one side of the parabola if I want. I'm just showing you, you know, it works both ways, all right? So what I'm going to do is those points where they hit the curve, the parabola curve, I'm going to drop them down to the XY line now, okay? So I'm going to drop, for example, this one here, which is quite close to the end, all right? I'm going to drop this one down here. Drop this one down. And drop this one down, okay? So I have them drop down now. And I'm going to transfer them into the actual plan view now from the end view, okay? As you know from basic orthographic, all right, we simply bring those points from the XY line now at 45 degrees down into the plan view. Again, I'll continue those down in the same color, okay? Now, again, the points are a little bit tight there, but doesn't matter. You'll get the idea of it, hopefully. And we're taking them at 45 degrees there. And let's say we take that one down there. Lovely. Take this one down here. Lovely. Here. Lovely. And here. Okay. That H1 line was nearly close to, very close to the bottom, so that line runs very tight. So what I'm going to do now is I'm going to take those points and I'm going to run them all the way over to the line AC. Okay? All the way over to the line AC. And don't worry about, just draw them across, okay? And then we can locate the points that we need in a moment. Lovely. Okay, all right. Well, there a couple of little wobbles there in the line. Now, I'm going to locate the points, all right? So, for example, I say, right, this is H4, all right? So, my projections for H4, where they meet H4, that's going to be my point. So, I'm going to have a point there and there. Okay, point E is a point. H3, where the H3 projections come down and across and meet the H3 line, they're my points for H3. For H2, down, across to meet the H2 line, like so. And then finally the H1, right down there, and we get H1 there and there, quite close to the edge. Okay, now that's lovely. What we have there now, we can join everything up there. Okay, we have the curve in our plan view for the shell in the most part. Okay. Lovely. Okay, so I have that curve there. Now I want to find this little front bit. What I'm going to do is, you see, I'm going to use the blue here now. I'm going to divide up this section between the point E and the line B into 3 equal parts, okay? For me, it just so happens the distance from E to the line B is 21, so I'll go 7 and 7, yeah? So that'll give me 3 equal parts, and all I'm going to do, and if the line's pre-drawn, is I'm going to draw straight down here into the plan view like so, all right? All the way down to the bottom line of the plan view. Don't worry about anything else there now. Just draw that straight on down, all right? Lovely. Okay, now what am I going to do? I'm taking now the distances between the curve and the cut line. Okay? So the shape that we generate in the plan is always relevant between the defining curve and the defining line. On this side, it was the curve and the XY line. On this part here, it was the curve and the line that cuts the object. Okay? That makes sense? I hope it does, right? I'm going to call this H5 and H6. Okay? I'm going to mark down H5 and H6, all right? So I get it on my compass. I take H5. I mark down H5 like so. And I, again, little arrow, and I write H5. And then H6, I will take the length of the H6 line that I've just discovered. Okay. Very happy with that. Mark it down. and mark your H6. Now what I'm going to do is, again, straight across now, use your T-square, draw it across to hit the parabola on both sides. Okay, project those points straight down. Okay, I think you're getting the picture now probably that this is exactly the same now as the other method. Project those points straight down to hit the XY line. And what we want to do after that, guys, is we want to then bring them at 45 degrees down to the plan view. Okay, and likewise on the other side. Okay, and then what I'm going to do is I'm going to bring them lines straight across all the way to the end. Over here. The full length of the plan view. Bring them all the way over. Okay? And don't worry if they line up ever so slightly. Likewise there. And then here down at the bottom, we'll have the same crack down here. And likewise down here. And we are now going to find the points that are defining the curve. So there we go there. It intersects. So the line for H5 and H6, let's say take H6 first, bring them down, bring them across, intersect the line coming down from H6, likewise from H5. We get the points there, 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 and now all we have to do is join them up. So, curve it around, and what we have now as a result of that, guys, is we have our plan view of our shell shape. Now, what else could be asked in that? You could be asked to find the true shape of a surface. You could be asked to find the cut shape of a surface. You know, there are little variations like that. Who knows? Okay. But now, what you've got there in one page, guys, is you have the actual bones, I would say more than the bones, all right, of a full area, all right, on one page. Okay. And it might be useful, all right, to take a little snapshot of that when I zoom back out here now in a moment, because I won't be happy until everything's at least colored in as neatly for the time being as possible. Like so. Okay. I'll get everything out of the way here. I will do a quick 2-minute recap and then we're done. All right. Right. Zoom back out. There we go. Right. So this is our worksheet complete. I'll just tip that back up. There you go. And right. So hopefully you can get a full shot of that, lads. Maybe I have to go a little bit higher. Yeah, that's a bit better. Okay. Focus and lock the lens. Now, okay. Here we go. Hyperboloid revolution. All right. We went through tangential asymptote method. Tangent in the plan view, divided up, project the points around the center line of the circle there. Project your points up to your asymptote to the elevation. We were given the length of the true length of the asymptote. We had to find the height of the hyperboloid revolution as a result of that. We went through that, okay. And then what we did then was we formed the curve as a result, and so on. All right. Next thing we went on to type 2, the hyperbolic paraboloid. This Pringle shape, we were given the elements here, A, B, C, and D in the plan view and in the elevation. And what we did was we constructed an ellipse around it as instructed in the actual conditions of the question. All right, ellipse standard construction. What we did then is we divided up the surface of the elements A, B, C, and D, and we projected them up to the elevation, and we found the curve of the top surface containing the saddle point. Then for the under curve, what we did was we extended each of those points on to hit the ellipse surface, the edge of the ellipse, and then we project up the points from the ellipse curve, extend the lines on out, and we get the points for the undercurve. Okay, that's the hyperbolic paraboloid. And then lastly, then we had the parabolic translation, where we have this generating parabola, which is actually translating along the conditions of two other parabolas, basically the line E and D. It's translating along that line, okay, and it's forming the shape C and D as it does so as a result. And as you've seen in the formation of the plan view just a few moments ago, that's how we ended up getting that shape there. Key thing here, taking the heights, labeling, projecting them correctly here from point B down in the end view, and then taking the width and projecting them back into the plan view, lining them up correctly, getting your points and so on, and it should all work out. Lads, look, I hope that's a help to you. Take a screenshot of that if you need to. All right, apologies now if there's a little bit of a shadow there on the top of it, only I have a kind of a little thing here propping up my visualizer. So look, wishing you a good day. All right, get out, get a bit of fresh air. All right, keep your distance, and look, it's a quiet time for everyone if you're at home and that, so make use of the time as best you can, but remember to chill, you know, have the crack as well, and we'll see you again tomorrow at 2 p.m. So I'll be covering conic sections then, which will lead on from this a little bit with some of the parabola and ellipse stuff. So until then, lads, good afternoon, good evening, and good night.